the sine function, the opposite over the hypotenuse, and then just solve from there. Because we know the distance that it goes up, and that was this b right here, the distance that it goes up the slope. Okay, other questions? Okay, so let's look at question 2 now, FA and EA. FA is going to be a little bit different now. If we look at what's happening here, the applied force is going up. Working against it, we have the force of kinetic friction. We also have Fgx prime that we talked about, that in our tilted coordinate system, there's a component of gravity that's pushing down the slope. And what's left over is the net force. And so we can get, if we can analyze the forces in that direction, we can see that the net force is equal to F sub A going in the same direction. Then we come back, F sub K, and we come back, Fgx. And I do it this way rather than giving it straight out as a formula, because this is an easier way of seeing how to get this formula out of it. Looking at what forces are acting on it and what's happening. So, since we need F of A, we have the net force plus F sub K plus Fgx prime. That's equal to F sub A. And that's what we need, F sub A. Well, here we know that this is mass times acceleration. We can get that. We know that this is this is the formula that you'll be given this formula again. U sub K, mg cosine of the angle. Now the angle does make a difference. And here we know that this is just mg sine of the angle. So now we're able to calculate this applied force. It's a little more complicated because now it's being divided up into, some of it's being used to overcome gravity, some to overcome friction, and some to overcome or to give it the object a net acceleration. So we can say Fa, it's equal to 2 times 3, that's from the applied force, plus F sub K, which is 0.2 times 2 times 10 times the friction that's the friction of 10, and cosine of 30 degrees plus Fgx, which is 2 times 10 times the sine of 30 degrees. That's 20. So this one becomes 10. This is 1/2, that's 2. This one becomes 6. And this one becomes 4 times cosine of 30 degrees, which is what, 0.867 something. So it's going to be a little bit more than what, about 3.5. Yeah, about 3.46. So this evaluates to 3.46. So now we have our applied force. It's 6 plus 3.46 plus 10. So we have about 19.46 newtons. That's our applied force.
Wait,
Again, I'm sorry.
The sine part?
Right.
Why is that 10?
Okay, we're using gravity. If it's the approximation, we're using that. I know it's really 9.8, but we're using it to make the calculations easier. It's about 9.6. I mean, it's about 10 rather than 9.8. And that's what I've been doing throughout the problems here, just to make our life easier. We know it's not that, but it doesn't really affect the calculations any if we use something to make our life a little easier there with that. Okay, so are there questions about this applied force right here? Okay, now after this, the energy to overcome the energy delivered by that force becomes very easy to do because we've already gotten the distance. It's going to be giving more energy because now it's overcoming friction as well. I'm sorry?
I'm still over here.
Okay, okay. So So we have, now we have energy to overcome, well, the applied energy, the energy from the applied force. We have, again, F sub A times the distance that it's moved. F sub A we've calculated now to be 19.46. We could run it at 19.5, but we'll keep it this way. And we've already calculated that it's gone 13.5. So about, what, 270, almost 270.
262.
Okay, thank you. Okay, so 262.7 joules. We know that's going to be divided up between the kinetic energy, the potential energy, and the work to overcome friction, and we can use that fact to make sure that we solve things correctly. If we haven't, we're not going to get the same sum. It might be a little bit different due to rounding differences. If you'd rounded it up to 19.5, which would be acceptable, it's going to be a little bit different, but it shouldn't be a large difference. Okay, so questions so far about this example? Okay,
The next question was KE
Yeah.
final, PE
Okay,
final,
thanks.
ME final.
okay.
Yeah, but why?
Okay, so if you have a question, or if you're kind of,
Why do we have the sign and I got lost over here?
okay, this one, this is F sub k, and its formula is the mu sub k mg cosine of the angle. And that's where all that is. That's the mu sub k, the m, the approximation of gravity, and that. And this is that fgx prime that we showed how to get before, which is mg sine of the angle. That's the other force that it's having to overcome, and that's, again, the same things right there. Okay, let's go ahead and look now at part 3 with the kinetic energy and all of that.
Oh, okay.
Okay, so we have kinetic energy final. That's mv squared over 2, final squared over 2. It's going to be the same final velocity we calculated before because we have the same factors before. This is still 0. That's 3t. So vt is equal to 3t. So it's the same thing that we calculated in the last example. So I'm writing it a lot more quickly here. So again, that would be 2 over 2 times 9 squared. The kinetic energy doesn't change. In this case, it should be 81 joules. So that part remains the same. That's our final kinetic energy. Since it's had the same acceleration, and for the same 3 seconds, that part won't change. And in fact, the work to overcome friction really shouldn't change. Well, no, it will, because we have a different angle than we had before. Before, the frictional force was 4, now it's about 3.46. Okay, so that's the kinetic energy, but let's look at the potential energy. And we have 2 ways of getting it. We have 2 methods. And either one of them is going to work. Okay, so the first method, we have the potential energy final is equal to Fgx prime times the distance. And we calculated Fgx prime to be 10. So that's 10 times the distance of 13.5. So we get 135 joules as the final potential energy. A second method would be to say, okay, the potential energy final is equal to mgh final, where the mass is 2, gravity is 10, and we've calculated the height to be 6.75 earlier, and that works out to give us exactly 135 joules as well. So because they match up, we can feel pretty confident that we've done things correctly. So there are the two different ways of getting the potential energy final. By using the force that you had to work against times the distance you had to work against it. Yeah,
FGS is 10.
what is?
FGS.
Is, oh yeah, it is not 100, it's 10, yeah. And then that number there would not be correct, thank you. Okay, so, see, this is not only physics, it's psychics. You have to read what I was thinking, and I was thinking 10 when I wrote 100. Okay, okay, so now we have that, I want to leave this here. Okay, so let's get the work to overcome friction. We have two ways of doing that now that we've solved for the other two. We could say that the energy applied goes to the kinetic energy final plus the potential energy final plus the energy to overcome friction. That's true. And we could solve it this way as we did before, just by subtracting. It's going to give us a way to double check the other result that we get. That should equal the energy to overcome friction. That's one method, so we'll do that method first. We said the total energy that we gave to the system was 262.7 minus 81 minus 135. And that should give the energy to overcome friction. So what is this? 216, so it should be about, what is that, 46.7? That's one method, if I haven't made some mistake in this. Yeah, that looks right. Or we could say the energy to overcome friction is the force that we had to use to work against friction times the distance. And this was no longer 4, it was 3.46. We calculated that. Again, the distance stayed 13.5. And so before it was about 52, now it's going to go down, and that looks to be, just eyeballing, it looks like it's going to be pretty close, if not exactly the same number. I'm getting about 46.71, so it's about the same. And that just leaves us for this problem with one more thing to do, and that's to find the total amount of, or the average power that this applied force gives to the system. Okay, so the last one, the power, that's going to be E over T. In this case, that's the energy that the applied force applies divided by T. So we have, what is that, 262.7 divided by 3. Okay, cool, 87.6. Okay, so 87.6 joules per second, or watts. That's the average rate at which energy is delivered. Okay, so it was delivered at a faster rate, because this time it was a different applied force. It was a bigger applied force because it had more things to work against in order to have enough left over to give it the same 3 meters per second squared acceleration. Okay, we're almost out of time down here. If anybody has any questions about this example, yeah.
How would you recommend we tell apart kinetic energy final and potential energy final from energy to overcome friction, because they all have like subscript S?
Oh, well, when I was energy to overcome friction, well.
Because that looks like it would just be energy final.
Well, this is all one block. It's KE was for kinetic energy. So I guess I'm not sure because, oh, okay, right. When it's just like that, that's the energy to overcome friction. But this will be written together as one word, because it's one block of letters, kinetic energy final. But yeah, that's a good point, because here it stands for friction, that stands for final. But just by knowing that the K means that's going to be kinetic energy, and that means it's going to be a final value, and that's going to be just sub F for friction. Okay, yeah,
Okay, so the energy, the EA, energy applied, is the same as energy, because like before, you're doing EEs
Yeah.
and you just kind of,
right, but I'm just emphasizing where it's coming from in this case. Because for the example that I gave with, it had that initial kinetic energy, that's what supplied the energy, and that's what gave the applied force, was from that initial kinetic energy that dissipated into the other two types. In this case, it's maybe something like, maybe an additional energy or something pushing it, it's some unknown, does that answer your question, or?
yes, ma'am.
Okay.